Right now, millions of robots are already working around the world, not in research labs, not in small pilot programs, but in real factories, warehouses, hospitals, and logistics centers operating at full industrial scale. According to industry data, more than 4 million industrial robots are currently active inside manufacturing facilities worldwide. That number has more than doubled in the past decade, and projections suggest it could climb towards 7 to 8 million robots globally by the early 2030s. That trend alone tells us something important. The robotics revolution isn't something waiting in the future. It's already happening, but the way most investors understand robotics is still stuck in an outdated framework. Most people imagine robotics as machines, mechanical arms, autonomous vehicles, humanoid robots walking across stage demos. But that perspective misses the real economic shift, because the real value in robotics doesn't come from the machines themselves. It comes from the intelligence those machines create and who controls that intelligence. Every robot operating in the world today is collecting data. Every movement, every error, every correction, every edge case encountered in the real world, all of that information feeds back into the systems that control them. And those systems learn. The companies that own those learning systems don't just build robots. They build feedback loops, and feedback loops compound. This is the piece of the robotics story that most investors are mispricing, because when robotics becomes a learning system rather than a machine industry, the economics change dramatically. Hardware becomes infrastructure, data becomes the advantage, and intelligence becomes the moat. In this video, we're going to break down the robotics industry in a way most investors never see. Instead of treating robotics as a single category, we'll divide it into 4 distinct tiers. Each tier represents a different part of the system. Each tier captures value in a different way, and each tier compounds differently over time. Once you understand those layers, the robotics landscape becomes much clearer. At the end, we'll also build a portfolio across these 4 tiers and explore how a $10,000 investment could potentially compound into a multi-million-dollar portfolio over the long run if the robotics economy grows the way many analysts expect. But before we even talk about stocks, we need to address a problem that trips up most investors, because many people still believe robotics is something that will matter more 10 years from now, something that is still early, something that hasn't really arrived yet. That belief is understandable. For decades, robotics was expensive, slow, difficult to scale. Most machines only worked inside tightly controlled environments like automotive factories. They repeated the same movement thousands of times. And if something changed, engineers had to manually reprogram every single machine. That made robotics rigid and difficult to deploy widely. But that mental model no longer reflects reality. Today, robots are no longer isolated machines. They are connected systems. Each robot feeds information into a shared intelligence platform. Each improvement learned by one robot can instantly benefit thousands of others. Once that system exists, progress stops being linear. Instead of improving one machine at a time, entire fleets improve simultaneously. And that changes everything, because when robotics becomes software-like, scale behaves differently. Training intelligence might be expensive, but once the intelligence exists, deploying it across thousands or even millions of machines costs almost nothing. The marginal cost of intelligence collapses, which means the companies controlling that intelligence layer gain enormous leverage. This is why robotics rarely arrives in one dramatic moment. There's no single event where everything suddenly changes. Instead, progress builds quietly for years. Capabilities slowly improve. Costs gradually fall. And then suddenly, efficiency jumps. Looking backward, those jumps feel obvious. But while they're happening in real time, most investors underestimate them. That misunderstanding creates one of the biggest opportunities in the robotics market today. Because when investors treat robotics as a single trend, they miss how value actually spreads across the system. Not every robotics company benefits equally. Some layers of the system capture enormous value. Others become infrastructure. To understand where the real compounding happens, we need to break robotics into its 4 economic tiers. And once you see those tiers clearly, the investment map becomes much easier to navigate. Once you stop looking at robotics as a single industry and start seeing it as a layered system, the entire investment picture becomes clearer. Because value in robotics does not spread evenly. Some parts of the system scale slowly and others accelerate dramatically as automation spreads. To simplify the structure, we can divide robotics into 4 core tiers. Each tier performs a different role inside the system, and each tier captures value in a very different way. At the bottom of the stack is what we can call the muscle layer. This is where digital commands turn into physical movement. Robot arms, actuators, precision tools, mechanical systems that move, rotate, lift, cut, and manipulate objects in the real world. Nothing in robotics works without this layer. No matter how intelligent a system becomes, eventually something has to interact with the physical environment. And that interaction requires reliable mechanical execution. This is where companies like Boston Scientific fit naturally into the robotics ecosystem. At first glance, Boston Scientific may look like a healthcare company rather than a robotics company. But when you look closer at what their technology actually does, the connection becomes clear. Many of their systems operate as robotic tools designed to perform extremely precise physical actions inside the human body. These are not consumer robots. They are highly specialized robotic instruments used in medical procedures where tolerances are measured in millimeters and mistakes are unacceptable. Their systems convert digital instructions into controlled physical movement. Catheters rotate. Devices navigate complex biological structures. Energy is delivered to specific points with remarkable precision. Mechanically speaking, this follows the exact same logic as an industrial robot arm on a factory floor. The difference is simply scale. Industrial robots manipulate large physical objects. Medical robotic systems manipulate extremely small ones. But the fundamental role is the same. They provide the physical execution layer. This is why Tier 1 behaves differently from other parts of the robotics industry. Demand grows steadily as robotics adoption spreads. Hospitals adopt robotic assistance because it improves precision and consistency. Factories adopt automation for reliability and efficiency. But improvements in this tier tend to be incremental rather than explosive. Better engineering, more precise components, wider adoption, steady refinement, not sudden breakthroughs. That doesn't make this layer less important. In fact, it makes it foundational. Without reliable hardware, no robotic system can function. But from an investment standpoint, this layer typically compounds at a slower and more predictable pace. It benefits from scale. It benefits from long-term demand. But it rarely produces the dramatic upside associated with higher layers of the robotics stack. That steady profile is reflected in how the market tends to evaluate companies like Boston Scientific. Analysts generally view the company as a stable long-term growth business. The outlook often includes moderate upside expectations driven by expanding adoption and consistent product innovation rather than speculative technological breakthroughs. And that stability is exactly the role this tier plays. Tier 1 creates the floor of the robotics ecosystem. As automation spreads across industries, someone has to build the machines capable of interacting with the real world. That demand does not disappear. It grows gradually over time, but precise physical movement alone is not enough to make robotics transformative. A robot can move perfectly and still be useless if it doesn't understand what it's interacting with. To move beyond repetitive tasks, robots need perception. They need the ability to interpret their surroundings, to detect obstacles, to distinguish objects, to operate in environments that change constantly. And that capability brings us to the second tier of the robotics stack, the layer often described as the eyes and nerves of robotics. If the first layer of robotics provides the muscles, the second layer provides the senses. Because before a robot can make a decision, before it can move safely in a complex environment, it first needs to understand what it is seeing. This is where perception systems come in. Cameras, sensors, machine vision, imaging technologies that translate the physical world into digital information a machine can interpret. This layer is what allows robots to move beyond simple, repetitive environments. Inside a traditional factory, robots were often placed inside cages. Their environment was carefully controlled. Every object appeared in the same location every time. But the real world doesn't behave that way. Warehouses change constantly. Hospitals are unpredictable. Outdoor environments are chaotic. Objects move. Lighting changes. Unexpected obstacles appear. Without reliable perception, a robot operating in those conditions becomes useless. It either slows down dramatically or fails entirely. This is why the perception layer has become one of the most important parts of modern robotics. A robot that can see clearly can adapt. A robot that cannot see clearly must be controlled. And that difference determines whether robotics can scale across industries. One company sitting right at the center of this perception layer is Teledyne Technologies. Teledyne builds advanced imaging and sensing systems designed to give machines perception beyond what the human eye can achieve. Their technologies include thermal imaging, infrared sensors, multispectral cameras, high-precision machine vision systems. These tools allow robots to detect heat signatures, identify objects in darkness, and interpret environments filled with visual noise. In robotics, this capability is not about producing prettier images. It's about producing reliable information. A robot navigating a warehouse needs to identify obstacles instantly. An autonomous system operating in smoke or fog must still function accurately. A medical robot must detect extremely small variations in tissue. In all of these scenarios, perception becomes the limiting factor, and companies that solve bottlenecks tend to capture durable value. Teledyne's advantage lies in the depth of its technology stack. Instead of producing a single component, the company builds integrated perception systems, sensors, optics, signal processing, software that converts raw visual data into usable information. That end-to-end approach is what makes perception reliable at scale. And reliability matters more than cost in environments where failure is expensive. From an economic standpoint, this layer behaves differently from basic robotics hardware. As robots move into more complicated environments, demand for high-quality sensing increases dramatically. Each new autonomous system requires better perception. Each new environment creates additional data. And each improvement in sensing capability unlocks new use cases for robotics. This is why the perception layer tends to compound faster than pure hardware. It sits closer to intelligence, but still benefits from the physical expansion of automation. In financial markets, this position often places companies like Teledyne in a middle layer of robotics investing. They are not purely hardware manufacturers, but they are also not the companies building the artificial intelligence models themselves. Instead, they provide a critical bridge between physical machines and digital intelligence. And bridges often become extremely valuable in complex systems because if perception fails, the entire robotic system breaks down. However, perception alone still doesn't make decisions. Sensors collect massive amounts of data. Cameras capture images, signals stream continuously. But something still needs to interpret that information and decide what to do next. That is where the third layer of robotics begins, the part of the system where intelligence actually lives. The brain of robotics, and that is where the largest concentration of value often appears. Once robots can move and once they can see, the next question becomes obvious. How do they decide what to do? Because perception alone only produces data, images, signals, environmental information, but data without interpretation is useless. Somewhere in the system, that information must be processed, analyzed, and turned into decisions. That layer is the brain of robotics. This is where intelligence actually lives. It includes the computing platforms, training systems, simulation environments, and orchestration software that determine how robots behave. And right now, one company sits closer to the center of this layer than almost any other, NVIDIA. Interestingly, NVIDIA does not build robots. It doesn't manufacture robotic arms. It doesn't produce industrial machines. Instead, it provides the infrastructure that allows robots to think. Modern robots process enormous amounts of data every second. Camera feeds, sensor signals, environmental maps, motion planning. All of that information must be interpreted instantly. That requires massive computing power. NVIDIA's chips are designed specifically for this type of workload. But the real advantage goes beyond hardware. The company has built an entire ecosystem around robotics intelligence. One of the most important pieces of that ecosystem is simulation, because most robotics training does not happen in the real world first. It happens inside virtual environments. Before a robot ever touches a factory floor or warehouse, engineers can create a digital twin of the environment, a virtual replica. Inside that digital world, the robot can run through thousands of scenarios. It can learn how to navigate obstacles, test movements, fail repeatedly, improve its behavior, all without risking damage to real equipment. What might take years of trial and error in the physical world can be compressed into weeks inside simulation. And once the intelligence improves, that improvement can be deployed instantly across entire fleets of robots. Thousands of machines can receive the same update simultaneously. This is the learning loop that makes robotics powerful. Every robot collects data. That data improves the models. The improved models update every robot. And the cycle repeats. This is why the intelligence layer tends to capture the largest share of long-term value, because improvements at this level amplify every other part of the system. Better models make sensors more useful. Better models make hardware more efficient. Better models allow robots to operate in more environments. And once a platform reaches scale, competitors struggle to catch up. This is how ecosystems create moats. Some investors naturally question whether a company like NVIDIA can continue growing when it is already so large. That skepticism is reasonable, but platform companies behave differently from traditional manufacturers. Their growth doesn't come from selling individual units one at a time. It comes from becoming the default infrastructure for an entire industry. When developers build their systems on a particular platform, switching becomes difficult. As robotics expands into new industries, the same intelligence infrastructure can be reused repeatedly. Factories, warehouses, autonomous vehicles, healthcare robotics, infrastructure maintenance. Each new use case increases the value of the platform. That is why analysts often remain optimistic about NVIDIA's long-term role in robotics and artificial intelligence. Not because of short-term hype, but because of the leverage created by owning the intelligence layer. However, even the most advanced intelligence platform cannot create value by itself. Software must eventually be deployed in the real world. Robots must actually perform tasks. Systems must operate at scale. And that final step leads to the fourth and final tier of the robotics ecosystem. The companies that operate robotic systems in real-world businesses every day. And that is where the robotics story becomes less about technology and more about operational advantage. The final layer of the robotic system is the one most people overlook. When people think about robotics, they usually imagine the companies building machines or the companies developing artificial intelligence. What they rarely think about are the companies actually running robotics at massive scale every single day as part of their core business. But this layer is where the technology finally turns into real economic power. And one of the clearest examples of this tier is Amazon. Across its global logistics network, Amazon operates one of the largest robotic systems in the world. Inside its fulfillment centers, thousands of robots work continuously. Robots moving shelves, robots sorting packages, robots navigating through massive warehouse floors, robots working side by side with human employees. But the advantage isn't any single robot. It's how all of those machines work together as a coordinated system. Amazon doesn't win because it owns one unique robot. It wins because it integrates robotics into the entire operating engine of its business. Inventory movement, package routing, picking, sorting, storage optimization, all of it is managed through centralized software systems that constantly rebalance the flow of goods. If one area of the warehouse becomes congested, the system adjusts. If demand spikes in a particular region, logistics routes adapt. If a robot slows down, another robot takes over the task. This coordination is where robotics becomes operational leverage. Each small improvement compounds. Faster picking reduces delays. Better routing reduces congestion. Fewer handling steps reduce labor costs. Individually, those improvements might look minor, but across millions of orders every day, they become enormous. This is also why this tier is incredibly difficult for competitors to replicate. Anyone can buy similar robots. Anyone can license similar software. But building a system that has evolved through years of real operational data is much harder. The workflows, the logistics patterns, the coordination algorithms, all of that knowledge accumulates slowly over time, and that accumulated experience becomes a competitive moat. From an investment perspective, Tier 4 companies often don't look like robotics companies at all. Amazon isn't marketed as a robotics firm. It's seen as an e-commerce and cloud computing company. But robotics quietly powers much of its efficiency advantage: faster deliveries, lower fulfillment costs, more resilient logistics networks. Automation improves the entire operating engine, and investors ultimately benefit from that operational leverage. When you step back and look at the entire system, the four tiers begin to make sense together. Tier 1, execution. Boston Scientific represents the physical precision layer. Tier 2, perception. Teledyne provides the sensors and vision systems that allow robots to understand their environment. Intelligence. NVIDIA supplies the computing infrastructure and learning platforms that allow robots to think. Tier 4, operation. Amazon deploys robotics at massive scale to create real economic efficiency. These companies are not competing with each other. They reinforce each other. Each tier depends on the one below it and amplifies the one above it. And that is why robotics should not be viewed as a single investment theme. It is an ecosystem. Now let's imagine building a portfolio across these four layers. In this example structure, Boston Scientific holds 20% of the portfolio, representing the foundational execution layer. Teledyne also receives 20%, capturing the perception layer as robots expand into complex environments. The largest weight goes to NVIDIA at 40%, reflecting the leverage created by controlling the intelligence layer. Finally, Amazon holds 20%, representing operational deployment and real-world efficiency. Based on historical performance and adjusted long-term expectations, this structure produces an estimated average annual return around 25.9%. To understand the power of that compounding, let's walk through the projections. If you start with a $10,000 investment, after 1 year, the portfolio could grow to roughly $12,592. After 10 years, the projection reaches about $100,218. At that point, the investment is already multiplied roughly 10 times. But the more interesting question is, what happens if you stay invested? After 20 years, the projection reaches approximately $1 million. That represents nearly a 100 times return, driven purely by compounding. And if the same growth rate continues over 30 years, the model suggests a valuation above $10 million. That's roughly a 1,000 times increase from the original investment. Of course, projections are never guarantees. Markets change, technology evolves, competition appears, but the larger point remains important. Robotics is not a single product trend. It is the automation of physical work across the global economy. And companies that sit in the critical layers of that system may compound for decades as automation becomes the default way work gets done. If you want to see how a simple $5 per day investment can grow into a portfolio generating more than $8,000 per month in dividend income, click the video on the screen and I'll show you exactly how it works.